Hi. Today we're going to look at chain signatures on Near Protocol, a really exciting feature that allows you to sign ECDSA signatures and soon ED25519 signatures for any destination chain. So you can broadcast transactions to Bitcoin, Ethereum, any other EVM chain. So chain signatures, these are threshold signatures controlled by Near accounts and smart contracts. So you will need a Near account or a Near smart contract to basically call the chain signatures contract, which sits on Near protocol, in order to get a valid signature. This contract is run as an MPC, so multi-party computation, by a number of trusted sources. We have a very simple API to trigger the signing of a payload for any key type. Right now, we currently support ECDSA, but coming soon is ED25519 and other signature types. So this is the method signature for the call. You basically pass in the payload of bytes that you'd like to have signed, and that's basically just a hash of the transaction that you would want to sign. A key derivation. It's kind of like a hardware offset for a ledger wallet. So this key derivation could be, it could be mat.near plus Ethereum, comma 1, comma 2, comma 3, and that would make different Ethereum addresses. And ultimately produce different Ethereum signatures. And key type is, of course, like the different types of keys that we're going to have coming soon. So basically, we have a user calling from the Near account. We're going to call basically to sign a payload, and then it's going to go out to this MPC network, which is a bunch of trusted sources that are running computation, each one having only a piece of the key to start the signing process, and they're going to return a completed signature. And then the Near account is going to receive the signature. So at this point, the Near account, being on a client, can basically take an unsigned transaction, combine it with this received signature, and they can send a transaction to the destination chain. So you would do this on Ethereum by, for example, just broadcasting, ETH send raw transaction, and you would send the signed transaction data to the Ethereum blockchain, broadcast it, and it would get verified, and funds would move. So chain signatures enable smart contracts to sign transactions. So you can make chain agnostic applications. You can do DeFi on Bitcoin by basically moving Bitcoin into a chain signatures account, and then you can credit a synthetic on Near or on other chains as well. And you can do multi-chain account abstraction. So very, very cool stuff. And I'm going to proceed into a workshop on how to use chain signatures and actually how to do some chain signatures with smart contracts and talk a little bit about the application logic towards the end of the tutorial. Hi, today we're going to go over a tutorial on how to use Near Protocol's chain signatures. What we're going to be doing is we're going to be creating some derived accounts for Ethereum, and we're going to be sending some ETH from those derived accounts to another Ethereum address. Then we're going to be deploying an NFT contract for that derived account. And finally, we're going to deploy a Near contract that will create a new Ethereum derived account. And then we're going to deploy the NFT contract to that account. Everything that you need for this workshop is here in this chainsig script repo. It's github.com/near-examples/chainsig-script. So all we're going to do is we're just going to run the script by just saying yarn start and then typing in some commands. And we're just going to go ahead and start doing that now. So I'm just going to switch over to code here, and basically I'm going to type yarn start EA, which is going to give me a derived Ethereum account and some extra information here. So the Near account ID that I'm calling from is this account ID. The MPC contract is the Near chain signatures contract, so that's that. The public key for the Near chain signatures contract is provided here, and basically the path that I'm using to create this derived account is Ethereum, comma 1. So might make sense to just look at how derived accounts are made. So basically you have the Near account ID you're calling from plus a path variable, in this case Ethereum, comma 1, and that will produce a derived account. Now this path variable, this can change. And so you can produce many derived accounts from one single Near account. So you just say Ethereum, comma 2, Ethereum, comma 3, and Ethereum, comma n, and you would get a different derived account. So that's basically how that works. And then you might be wondering, where did all this stuff come from? The Near account ID and the MPC contract ID? Well, they come from the environment variables here. So in your project, after you clone this repo, at the very least, you'll have to create this first set of environment variables. And that was sort of the part that I kind of brushed over here. So we're already using some commands, we're already making an Ethereum account. Now, what about sending some ETH? So that's an easy command. ETX is basically just, do an Ethereum transaction for me and send some ETH, and it's pre-configured to send ETH to a default address and a certain amount. So you can see that it's gotten the balance here, and it's basically sending 0.001 ETH from this account to this account. So you can choose to accept that. Now, what's this sign payload part? So we're calling the near MPC contract to basically sign the payload of the Ethereum transaction that we want to execute. So we've created in this script, we've created client side the unsigned Ethereum transaction. We've hashed it, we've gotten the payload, and now we're passing that payload to be signed to the MPC contract. And as you can see, the MPC contract responded. It responded with some signature information here, but the script basically took the signature data and it attached it to that unsigned Ethereum transaction, and it already broadcast it. So the transaction hash is right here, and we also have a link to the Explorer here. I'm going to open that up now, and we'll just zoom in. And you can see that the transaction was a success. 0.001 ETH was sent from this address to this address. So that's great. So we've already done a couple of things. We've created a derived account, and we've already called the near MPC contract. And this is what a call looks like. So you take your near account and you call the MPC contract with the path. Remember, Ethereum, 1 was the one that I used for my derived Ethereum account. The payload, which was the hash of the unsigned transaction that we wanted to get the signature for. And key version is something that will just be used in the future. So we call sign with this request object, and we get the signature for the derived account. Now, if you're building a call to the MPC contract yourself and you're trying to get the signature, I can go ahead and show you where that code is in this project. It's under source and it's under near. A full dive into the code is kind of outside the scope of this video, but you can see that the sign call is here, and there's an args object. There's a little bit of sort of configuration done to support a different call, but you'll be able to follow it pretty quickly if you dive into the code after this video. I'm just kind of generally showing you how everything works. So the next example, which is really kind of interesting, is deploying an EVM contract. So we're going to do a deployment, and we're going to interact with the EVM contract. And there's a few extra commands in order to just speed up the deployment of an EVM contract and the interaction with the contract. So I'm going to hit yarn start -D to deploy a pre-built NFT binary. And you can see right away it's asking me, do you want to deploy 21,000 bytes or whatever to this address? So I'm going to go ahead and I'm going to say yes. And once again, we're signing a payload. So we're calling that MPC contract. We're just signing a payload, but the Ethereum transaction is actually going to deploy bytecode now to a new account. This is a new address that is just a contract deployment address off of my Ethereum derived address. Now it's going to set my Ethereum derived address as the owner of that contract. So what that means is that only my Ethereum derived address, by calling the MPC contract, will be able to create the signatures necessary to mint NFTs, right? So because it's the owner of the NFT contract. So let's just go ahead and verify that deployed successfully. So we've got this new address. It's a contract. I'm not sure if we can see the contract bytes, but it looks like it's deployed okay. And I'm just going to copy that address, and I usually just kind of stick that in my environment variables folder, just so I know that all of this information here, all of this configuration, created a derived Ethereum account, which I can easily access with this command, -EA. I can see my Ethereum account, so that's the derived account using Ethereum 1 and this near account ID. But I don't have an easy way to get that contract ID unless I go to the Explorer and stuff. So I'm just going to save it here. So I know there's an NFT contract here. And if I follow along with the README here, you can take the contract address from the console result, and we can call to the Ethereum contract. We can call using a -2 argument. And I'll go get that address. and I'm going to paste that in. So what we're going to do is we're going to call, and the default is to call mint on that contract. Now remember, we are calling from the Ethereum derived account, so we are the owner of that newly deployed contract, so we can call the mint function. So it's going to ask, do we want to do this, and do we want to mint? And I have included just like a default address there. So I'll say, yeah, I want to mint an NFT to that address. Okay, so we're going to go ahead, and once again, we're calling the MPC contract, but we're actually, we have an unsigned Ethereum transaction payload that is this mint call. So we're calling this mint call with this argument of this address. So once that's done, we can go ahead, check on the Explorer. It's pending right now, but it should finish soon. But what we can also do is there's also a built-in command to view specifically the NFT balance. So what we're going to do is we're going to do the view call there, and we're gonna go ahead and we're gonna view for that NFT. And as we can see, the function balance of address returns this with args. And again, it's that default address that we minted the NFT to. The view result is 1. So we can also mint another one, and we can see how that goes. And then, of course, our NFT balance should be 2 for that address. So just showing you how this works. And remember, like we're not really using any Ethereum, account directly. We're just getting a signature for an Ethereum transaction, and then we're broadcasting a raw signed transaction payload to the Ethereum blockchain. Now you might wonder, where's all the ETH coming from? Well, I've pre-funded that address. So when you first create your address, so when you come to this point, probably to send some ETH, your balance is going to say 0, and it's going to say insufficient funds. So it'll tell you, it'll indicate that you have to fund that. So you just have to send some Sepolia ETH to that address. So while I was talking, we got back the balance of the address, and we minted 2 NFTs. So naturally, our view result is 2. So let's quickly recap what we've done. So we have, in step 1, we have called from a Near account to the Near MPC contract, and we got a signature for the derived account. Using that signature, we took the derived Ethereum account and we deployed an NFT contract, and that deployed NFT contract created a new a new contract account off of that original Ethereum account. And the derived account, though, is the owner of that contract. So it's the NFT owner in that contract, and only this derived EVM account can actually mint NFTs. So in step 2, the Near account calls the MPC contract again, and it gets a signature for a mint transaction. And then calling that derived EVM account once again, we basically attach that signature to the mint transaction. We broadcast that, and then an NFT is minted to any address that we wanna mint the NFT to. In our last example, what we're going to do is we're going to basically take a Near account. We're going to be calling a Near custom contract. We'll call it the NCC. And this custom contract will be the one that calls the MPC contract via a cross-contract call. And then we're going to get a derived account that is based on the Near custom contract's Near account ID plus the path variable. So it's important to note that the derived account, the derived EVM account that we're getting this time, is no longer a direct derivation from the Near account. It's actually coming from the Near custom contract account. So in order to get anything done with the derived EVM account now, we now have to call through the Near custom contract. So you could think of it as like our gatekeeper or our application logic or our access control logic prior to us getting anything done with that derived EVM account. So step 1, just like the previous example where we deployed the EVM contract directly from our derived account from our Near account, step 1 is to deploy the NFT contract. So what we're going to do is we're going to use the Near account, call the custom contract. That's going to call the MPC contract, and we'll get a signature. And then what we're going to do is we're going to deploy that NFT contract. And remember, the DA, the derived account, is actually the owner of the NFT contract, but it's now this derived account is based off of the Near custom contract. So why did we do this? Well, now we can let any Near account call the Near custom contract, provided that they satisfy the application logic and pay 1 Near token. And after doing that, they will be able to call the the near custom contract will call the MPC contract on their behalf and generate the necessary signature for the mint transaction. That signature can be passed safely all the way back to the client, which will use the derived EVM account and say, hey, I want to mint that NFT to to my address, right? So in this sense, basically what we're doing is we're from any near account, we're paying one near to mint an NFT on Ethereum. So that's sort of like the really cool logic there. Is that we're basically able to open up this near application, this near smart contract to any near account now, and they'll be able to mint this NFT on an EVM chain. So that's kind of cool, and we'll jump into the code in just a sec. Okay, so we're back here looking at the README, and we want to call a near contract to sign a call for an EVM account. So this is a pretty advanced tutorial. There's a lot of moving parts. And I've explained a little bit about going over the diagram about access control and protocol application logic. So what we're doing is we really have our protocol logic inside a near account, and then that near account is kind of like the gatekeeper for what that EVM derived account can and cannot do. And the near contract features are explained a little bit here. I'll go over them in the code as well. So basically, we have these public RLP encoded method names. This is basically just the mint method encoded here in an array, and that's because we need to know which EVM methods are safe and able to be called by the public. We have the MPC contract ID, which we're going to call via a cross contract call, and then we have the cost of a public call to the mint method, and we're gonna call that one near token. We have a struct here, which is the sign request. Remember that payload path and key version that you saw before. And then what we have is we have an external contract call that we're calling MPC here, and that's to call the sign method of the MPC contract, and that's going to return a near promise. So if we jump down into the actual smart contract itself, the smart contract accepts some arguments that look a little different. One of them is RLP payload, and that's because we're going to actually take in an RLP encoded payload, and we're going to hash it using the kekak here inside the contract. I'll explain why. It's just so that we can look at the publicly encoded method names, and we can just do a little bit of kind of inspection about the encoded transaction that the user's trying to sign. We have the path variable, so which account are you trying to derive from this? So we could have a near contract that actually is the gatekeeper for multiple EVM accounts, right? We don't just have to stick to just one. So clients could pass in Ethereum, comma 1000, and they could get a different, completely different NFT contract. But it's all the application logic about whether or not you can get a signature for that derived account. It's all here in this near contract. If it's not a public method, we do require that the near contract owner can create arbitrary EVM transactions. And this is what allows the owner to kind of pass through and deploy the EVM contract, but it stops any arbitrary near accounts from signing any arbitrary EVM transactions. So once we've passed our checks here, is it a public method? And if it's not a public method, you must be the owner. What we're doing is we're going to just encode the payload. We're also going to check the deposit requirement, and then we're going to do the cross contract call. So we're basically going to call the MPC contract ID. We just attach some gas, and we attach deposit here, the octo near, and then that's it. So we're going to see how that works by just following along with the commands from the README here as well. You're going to have to set up some more environment variables. So you'll also have to deploy the near contract yourself, but just follow along with this section here, and you can use cargo near to deploy the near contract. It's a handy little utility. And then this explains the protection there against arbitrary EVM transactions, and now we're going to start testing it. So we're going to call yarn start ETX. Whoops, that's wrong. ETX. And then we do have a balance. Oh, whoops, sorry. I am going to need to go back. Okay. Pause. So we are going to change these environment variables. We're going to make this true and true. So we want to call from the near proxy account. So we want to call from this account, and we want to call to the near proxy contract. So I'm just enabling these here, and I'm saying I'm going to call from the near proxy account, and I'm also going to call to the near proxy account. These are the same account, so I'm basically calling the near this near proxy contract as its owner. So I'm going to go ahead and follow the README. I'm going to call yarn start ETX. And you can see I have a very small balance of ETH here. If I don't have enough, then what I'll have to do is I'll have to change the environment variables, and I'll have to send ETH to this address. But I think I will have enough to deploy the contract. So what I'm going to do is I'm going to skip ahead, and I'm going to go back to the Ethereum EVM example, and I'm going to go ahead and deploy. Yeah, and you'll notice that I have way less ETH now. Why? Because my Ethereum address is completely different. It's different from the previous time that I deployed the EVM contract. Because remember, sorry, just a reminder, this derived account now is from the near custom contracts ID and the path, not the near account that I'm calling from. Okay, so what we're going to do, what we're going to do is we're going to deploy that contract. And it's going to ask me if I want to deploy those contract bytes. So I'm going to say yes. So that looks like it deployed successfully. So this is the new smart contract address right here. So once again, I'm going to put that under here. That's my ETH contract for the NFT. And then I'm just going to follow along, and I'm gonna call mint on that contract. Now this is where it gets interesting. I am calling. I am using the near proxy account to call. So I am calling from this near proxy account, which means I am the owner of the near contract account. So I should be able to do whatever I want. But I'm just going to do one call like this, and then I'm going to check the balance. And we're just going to verify that our NFT contract's deployed. And then I'm going to call from my original near account. So I'm going to call from an arbitrary near account, not the contract owner of the near contract. So now we're going to call that contract, but we're going to call from an arbitrary near account, and we'll see what that looks like here. You can see that the near account ID is different from the near proxy contract ID. So basically, we're calling from an arbitrary near account, and we'll need to pay that one near. And I assure you in the script, we are attaching that one near token to that near transaction to get the signature. So we're basically trading one near token for a signature that is valid for a derived account off of this near address, and then basically we're going to bring that all the way back to the client, and we're going to broadcast that transaction. So we've now minted our second NFT to the default address that was in the arguments there, but this time we did it by paying one near token to mint an NFT on an EVM chain to that address. So we're going to view the balance there, and it should be 2. And that's our view result too. So there you have it. We basically went all the way through, and we've actually called from any near account. We called a near custom contract. We paid one near token, which subsequently called the near NPC contract, got a signature for a mint transaction for a derived EVM account that was derived off of that custom contract. And sort of this custom contract served as the application protocol logic there, and was the gatekeeper, required one near token to call this mint transaction. Now this derived Ethereum account could broadcast that mint transaction, and we minted the NFT. So yeah, thanks for following along on the workshop, and I hope you have good success in your hackathon.